All right, so today we're going to start our first lesson in stoichiometry. But after today, we're just going to be dealing with mole to mole calculations. This is obviously, I usually start with the simplest of ideas or concepts when we do a new unit. So we're just going to do mole to mole calculations, and we use the coefficients at the beginning of each compound or element in the reaction. So we're going to be able to do those calculations, and then we'll be reviewing the basics of how to balance a chemical equation, which is what we learned in chemical reactions unit, so that should be easy. So um, for my Greek students, you may have already noticed what this word kind of breaks down to be. We're just measuring elements, and that's it. We're measuring elements using the coefficients in front of each piece of the chemical reaction. So by definition, here's the definition. This looks like a really good matching question. um, but it's just the study of quantities as it relates to chemical reactions. So that's it. That's it. It's very simple. We're going to be able to tell how much mass of one thing we can make if we are given a mass or a mole amount, a quantity of something else in the reaction. Okay, so when we take these chemical reactions, which is what we learned about last unit, we have, these pieces of it that you should already know. You know these are coefficients. You know this is how many atoms are right here. You know that this means that this element is actually a gas. We know that this means that we're combining these two together, and the arrow means to yield or to make, and then this is how many moles. Okay, well, you don't know that yet, but this is the coefficient of this compound. So yeah, you should pretty much be okay with this part of the equation, or the reaction. I'm sorry. So we're going to look at a balanced chemical equation in different ways. So first, we're going to look at the molecules. So this right here, this means that there is one molecule. So one molecule of N2 gas. Okay, so one of these. Here, so the reason why we wouldn't put like H6 is because it's not all one molecule. It's actually three molecules of two hydrogens bonded together, okay? And then that will yield two molecules of NH3 bonded together, okay? So we can look at it molecules. We can also look at this equation from mass. So if we have a certain amount of this and a certain amount of this, we can't make unlimited amounts of this, right? It depends on how much of this and this we have will determine how much this we can make. So according to the law, remember the law of conservation of atoms? Well, this is the law of conservation of mass. The mass on the reactant side must equal the mass of the product side. So just like the amount of atoms on the reactant side must equal the amount of atoms on the product side. So we can look at it from molecules, or we can look at it in the eyes of mass. Okay, they have to equal the same. And we will also look at it in moles, and this is the new thing you're learning. So you'll learn that the coefficient, okay, is how many moles of this you're using, okay, or you have. So for example, in this case, you have 1 mole of nitrogen, okay, and you have 3 moles of hydrogen, okay, and you have 2 moles of ammonium, okay. So this is what we're going to focus on in this unit, is this mole relationship. So for example, if you only have half of a mole of nitrogen, okay, then you'll have 1.5 moles of hydrogen reacting, and then you will be able to make 1 mole of ammonium. So basically, there's a relationship. This and this and this will always be a very specific ratio. Okay, if you had 2 moles of nitrogen, it would combine with 6 moles of hydrogen, making 2 moles of this product. Okay, I'm sorry, 4 moles of this product. So you see the relationship of the ratios, and we're going to use those ratios as in the calculation. So the coefficients represents the mole ratio, or represents the moles, and we can make a mole ratio, and this is what we're doing here. So there's a relationship between this and this. There's a relationship between this and this, and they're all related to each other as far as moles and ratios go. So think of it as, I guess, making a sandwich. Maybe you're making a sandwich with one piece of bread and 3 pieces of meat. We'll make 2 sandwiches. That doesn't make sense, but just stick with me. If you double this, then you're going to double this. So they're all related as far as amount of substances. So for example, for every 1 mole of nitrogen, you can produce 2 moles of ammonium. For every 3 moles of hydrogen, okay, you will need this much of nitrogen, this many moles of nitrogen to react. For every 2 moles of ammonium, you will need 3 moles at least to create that. Okay, so there's a mole ratio, and you're just using these numbers. Okay. All right, first example. So this is what your test will look like. If 3.86 moles of potassium reacts completely with excess water, how many moles of hydrogen would be produced? So first, the only difference, well, okay, there's a couple of differences from our mole questions, but one of the first obvious differences is that you actually have to create your own chemical equation. So first okay, you know you're going to have potassium, and you know it's going to react with water, okay? And then you will need to know how many moles of hydrogen would be produced. So hydrogen will be in the products. So we have potassium, okay? It's reacting with water, and it's going to yield, okay, I didn't want to give that away yet, but whatever. It's going to yield hydrogen and potassium hydroxide. So if you look over here, this is going to be the single replacement reaction. So that's how you predict, okay? I didn't want to give that, okay. So you're going to look and see if potassium is going to replace hydrogen. If you were to look at the, the activity series sheet, you would notice that it does replace it. And basically, we're looking at hydrogen, okay? We're looking at how much hydrogen would be produced, specifically how many moles of hydrogen are produced if you have this many moles of potassium. First, so we've made our chemical reaction in words. We need to bring it down to formula form, and then we need to look at the ratio, because obviously we're not going to have this many moles of anything because they have to be whole numbers, okay? So let's just start bringing down our formula, and I'll show you what I mean. So potassium is not a a diatomic element, so it's just K. And then water is water. You can write it H2O. I wouldn't have taken points off of it. It's just an easier way to compare potassium hydrogen on the activity series list. That's it. Okay, potassium hydroxide, so that's just an ionic compound, right? This is a metal, this is a non-metal, this is a +1 charge, this is a -1 charge. So it'll be KOH, and then hydrogen is a diatomic element, so it'll be H2. So we have our formula reaction, okay? So this is the second new step in the whole moles genre of chemistry. And we need to balance this. Once we balance this, we have our ratios of how much of each substance we will have in the reaction. So we have, there you go. You have 2 moles of potassium. So you have 2 potassiums here and 2 potassiums here. You have 4 hydrogens, okay, here, and you have 4 hydrogens here. So oxygens, we have 2 oxygens here, 2 oxygens here, so we're balanced. Okay, so moving on, balancing isn't like the main point of this, so we didn't do the tally method. I just kind of gave you the answers. But now we're here in our known and unknown. What you'll notice different from the beginning of the year when we did the known and unknown is this right here. it's always been the same unit or the same element that we've been calculating. However, in this unit, we're actually going from one type of element to the other. And that that mole to mole ratio is what we will use to jump from this element to this one in our dimensional analysis problem. So it's a little more complicated, but it's no big deal. So we're looking at sorry. So we're looking at the ratio of potassium and hydrogen only. We don't care about the other two because the question's not asking about it. So that's why I circled them. We're just going to ignore the rest. All right, so you always start with your known. That doesn't change, so that's at least familiar. And so whatever's up here must go here, okay? So that hasn't changed either. The only thing that's changing is this, okay? That when you've got this mole right here, you're going to do a mole to mole ratio. You'll hear me say that in class a lot. So the mole to mole ratio is the key to being able to jump from one type of element to another, okay? Usually we've always jumped from one unit to the other, but now we're jumping from one element to the other. So we are canceling out moles of potassium to get to moles of hydrogen. And that's actually what the question's asking, so we should be done with it by then. So this is the end of the equation, okay? So then you just take in your calculator. I'm sorry, this number came from the question, okay, which came from up here. This number down here, this 2 moles of potassium, that number came from this right here, okay? You're going to use these coefficients now as the moles. So this number came here, and this number actually came from right here. It's not just a conversion anymore. This is a ratio. So this 1, if this number would have been 3, you would have written 3 right here, okay? So then your answer is 1.93 moles of hydrogen gas, and that's your answer. All right, moving on. We're going to do another mole to mole calculation. So how many moles of aluminum will react with? So aluminum is, since it's reacting with something, that's going to be one of our reactants, obviously, with 0.512 moles of hydrochloric acid. So they don't give us any products. They just say aluminum is going to react with hydrochloric acid. So we're going to write our chemical equation. So it says aluminum in the problem is reacting with hydrochloric acid, okay? So now we need to predict our products. So in order to predict the products, we need to change hydrochloric acid to hydrogen chloride, okay? So remember hydro and ic, okay? The chlorine, the hydro and ic indicates that the ending of chlorine is ide, okay? So you would write hydrogen and chloride, you would look on the activity series sheet and find out if aluminum will replace hydrogen, and it does, okay? So then you would have aluminum chloride, okay? So aluminum and chloride would form that salt, okay? And the ionic bond, and then you would have hydrogen left over, okay? Hydrogen gas, and we will actually do this this reaction in class, and it's really fun. Okay, so aluminum is not a diatomic element, so we just bring it straight down. Hydrochloric acid is just HCl, and aluminum chloride, don't forget to write them up here and kind of cross down their charges so you don't mess this up. And then hydrogen gas. Hydrogen is a diatomic element. Okay, so now all we have to do is balance, and I believe I just give us the answer, so that's cool. So we have our ratios, okay? Now we need to do our known and unknown. So our known is what's given to us in the problem, this many moles of hydrochloric acid, okay? Our unknown is what it's asking for. It's asking for moles of aluminum, okay? So we're only looking at this and this, that's it. We don't really care about the products. So, okay, that's enough. All right, so we have our known. We always start with our known here, okay? And then whatever unit and element is up here must go down here. But we're going to use the coefficients as our ratios, okay? So that means mole of HCl, okay? Moles of HCl, we have 6 moles of HCl, okay? That will go down here, 6 moles of HCl. And then our unknown, will go up here, which will be 2 moles of aluminum. Let's see if I'm right. Yeah, look at me go. Okay, so we have our unknown up here. That means we know that's where we need to stop. Okay, our moles of hydrochloric acid, what's it called? Cancel. And then we just take 0.512 times 2 divided by 6 in your calculator. If you just do that, you'll be fine. Take 0.152 times 2 divided by 6 equal sign. Okay? And there's our answer. Okay, let's just do a quick example from the homework. We'll go ahead and do number 5 because the others like give you the equation, and so it's easy. All you have to do is balance and then do your problem. This one actually starts with nothing, and I think you'd rather me probably do one like this. Okay, so the question says, how many moles of oxygen are produced when 5.12 moles of magnesium chlorate decomposes into magnesium chloride and oxygen? So that's actually nice of them. They gave us our products and even told us what type of, let's see if the other one does. Yeah, all your homework problems give you what's the product. So, okay, we'll keep going with this one. So it's asking us to write the word equation. So how many moles of oxygen are produced? So that's on the product side when this many moles of magnesium chlorate. So word equation would be magnesium chlorate decomposes, no, sorry guys, decomposes, that means it's not reacting with anything. Okay, so magnesium chlorate decomposes, so this is just going to break down into two things. Magnesium chloride and oxygen. Okay, so now we just have to write out our answers. I just realized I need a polyatomic ion sheet. You guys have to forgive me for being so unorganized. I just graded y'all's midterms. Here's one. Yay. Okay. All right, I found one. Okay, so magnesium chlorate. So magnesium, let's just rip this off. All right, magnesium is here, okay, so it's in the second group. So magnesium is a +2 charge. Chlorate is on the polyatomic ion sheet. So that's chlorite. Chlorate is here, ClO3 minus 1. So ClO3 minus 1. So the charges will be brought down. Okay, so then our formula equation will be Mg ClO3 2. Okay. Decomposes into magnesium chloride. So magnesium is a +2 charge. We've determined that. Chloride is a -1 charge. Okay. So Cl with a -1, we bring the charges across, and we will have MgCl2. Okay. Plus oxygen. Oxygen is one of those diatomic elements, so it'll be O2. So we have our formula equation. We just need to balance it now. So we have 1 magnesium, 1 magnesium. Chlorate is broken down, so we can't, just count it. So we have 2 chlorines here, 2 chlorines here. And we have 6 oxygens here and 2 here. So we just need to add a 3 and we're balanced, okay? Okay, so we just need to write our known and unknown. Okay, so our known is from the question. We have 5.12 moles of magnesium chlorate. So 5.12 moles of MgClO3 2. Okay, and our unknown is how many moles of oxygen? So how many moles of oxygen, okay? So we always start with our known, just like in the beginning of the year. So 5.12 moles of MgClO3, 2, times, okay? And since, anyways, well, whatever is up here, I was going to say something, but I don't want to confuse you. Whatever's up here must go here, okay? So moles of MgClO3, 2, okay? So whatever our unknown is needs to go up here. We are already at moles, and we're going to end in moles, so we're going to do our moles of oxygen, okay? So now we're going to pull our numbers. We're going to pull it from the reaction now, okay? Instead of just doing 1 and some kind of constant, we're actually getting this ratio. We need a ratio. So we have moles of MgClO3, 2. That's actually 1, okay? So 1. And then oxygen, we have 3, okay? And we got the numbers here and here. Okay, so then you just, 5.12 times 3. And since that's 1, we're not going to write divided by 1 because it doesn't matter. It's 15.36. Significant figures, we're going to look at this. We have 1, 2, 3 significant figures. So 1, 2, 3, we need to cut it off here, round that up. So the actual answer is 15.4 moles of O2.